right, we're going to take a quick look at 8.6 hypothesis testing and confidence intervals. There isn't anything new here. We've done hypothesis testing and we've done confidence intervals. I just wanted to show you a really quick little tie-in. So this isn't a very important section. It's just it's a nice little tie-in on how those two relate when you're working with a not equal to. So it doesn't work 100% of the time with hypothesis testing that you could just instead do a confidence interval. But if the question is about not equal to, you can get away with just a confidence interval and make a generalization, about the hypothesis, do a hypothesis test. So let's take a look. 8.6. Basic statistics, we're on page 16 of the packet. And so if we take a look, we set our null and our alternative hypothesis. So it says, determine retention rates at a local college. A sample of 40 students were taken. Out of these 40, 32 were retained. At alpha equals 5% significance level, test the claim the college has a 70% retention rate. Verify it with a confidence interval. So before we actually find p hat, we're going to set up our null and our alternative hypothesis. So here's the null. It's just equal to 0.7. And then the alternative is that it's not that. Right? So that would mean it's p, so we get to go to z. Right? Anytime we're doing proportions, it's a z test. And so we set our critical values. Two-tailed, because it's not equal to, that means two tails. Set that one up, and we set that one up. And they wanted it at 5%, so you look up 5% two tails, and that gives you 1.96. So our critical value, our z-score, to beat is 1.960 on the top end and negative 1.960 on the bottom end. And remember, 0 is in the center now. Again, we're out of the chi-square. This back to z distribution. All right. So now letter C is we go ahead and calculate our z-score. To do that, we need a p hat minus p divided by the square root of PQ over N. So I'll tell you what, in the center of the board here, I'll write out all the stuff we're going to use. So N, in this case, was equal to 40 students. And P hat, we would calculate, that would be 32 divided by 40. That's actually 0.8. Right. What else do we need? So we have N. P was given as 70%. Q we figure out by doing 1 minus 0.7. That's 0.3. And that's everybody we need for this calculation. So let's do this. So Z is equal to 0.8 minus 0.7 divided by the square root of 0.7 times 0.3 divided by 40. All of that is under the square root sign. So when you calculate that, let's see, we get 0.1 on the top, right? But inside of that square root sign, you get 0.00523. Be careful, depending on your calculator, it might say 5.23 times 10 to the negative third, and that's just scientific notation. You got to put it back into standard, but moving the decimal 3 places to the left. All right. Then you actually take that square root. We get 0.1, and then on the bottom we get 0.07245, and it keeps going on for a while. We'll just end it at 7. And then when I divide that out, that is 1. So Z is equal to 1. We needed it to be bigger than 1.96 or less than negative 1.96. And so that didn't cut it. 1 is in the unshaded area, which means failed to reject the null. Failed to reject the null at the 5% significance level. And then the write-up would be, there is not enough evidence to show, we conclude the proportion of students is still 70%. It wasn't enough evidence. You could do it two ways. You could state what you just concluded. We conclude the proportion of students being retained is 70%. Or you can restate it as there is not enough evidence to conclude that it's not 0.7, which is fine. Either one is fine. All right? So this we've already done. That isn't anything new, and neither is this. Build a 95% confidence interval. So let's look at 95% confidence interval for this data. To do that, what do we need? We need p hat minus z, the z-score for 95% confidence interval, and times the square root of p hat q hat all over n, and then that's less than p, which is less than p hat, plus all that same stuff, the margin of error. Okay, so this z times the square root of p hat q hat divided by n is called the margin of error. It's going to be the same. So instead of writing all that out twice, a lot of times I just shortcut it to margin of error. All right? Okay, so, I didn't find q hat. Well, let's go ahead and find q hat. Q hat would have been 1 minus 0.8. That's pretty easy, right? You could probably do that without any work. 0.2. Okay, so let's figure out the 95% confidence interval for this thing. So we got 0.8 minus 1.960 times the square root of 0.8 times 0.2 divided by 40, and then that's less than p, and that's less than 0.8, plus all that same stuff, margin of error. All right, so again, I'll show the work, 1.960 there, but inside, when you do 0.8 times 0.2 divided by 40, you get 0.004 inside of the square root. And then you take that square root, and it becomes 0.0632, and then you multiply that by 1.960, and it becomes 0.124, and that's less than p, and that's less than 0.8. You know, all of this is still there. Less than p, less than 0.8, plus error. Less than p, less than 0.8, plus error. Less than p, less than 0.8, plus, now we can put the error down. The margin of error is 0.124. All right? And so now we subtract it from 80% and we add it to 80%. So we end up with 0.676 is less than p, which is less than 0.924. So that's our confidence interval. You might say, yeah, so what? We did those already, confidence intervals. That means if we were to redo this 100 times, a trial like this 100 times, 95 out of those 100 would actually contain the true mean. Well, check it out. 0.7. Now, a couple of things that I want to point out quickly here while it's on the board. This one, we used P and Q for our calculations on the standard error. This one, we used P hat and Q hat to make that. And so that's a difference, you know, that's a subtle difference. All right? So now, look, if this is inside of this 0.67 is less than 0.7, which is less than 0.924. That means if the null hypothesis is contained in the confidence interval, the 95% confidence interval, we could use this. So instead of doing this and that, we could use this alone with a two-tailed test. If this was our hypothesis, we could skip this and go to the confidence interval and go, all right, the null is contained in the confidence interval, so we fail to reject the null. So had this been 0.776 to 0.924, then we would have rejected the null, because then that wouldn't be contained in the confidence interval. And so it's a shortcut that can be used, but it often isn't, because a lot of times we want the write-up. We want the picture, we want the z-score, sometimes we want the p-values, and we want the whole write-up. But that's kind of a shortcut thing, or a confirmation. We could say, hey, look, that confirmed it. We found the same thing. We used slightly different numbers there, right? Because we were using p hat and q hat, so you'd look at it that way too. And then let's look at page 17. It's just another example, but this time they don't want you to go through all of this. They just want you to find the confidence interval and make a determination about the hypothesis. So we're going to set up the hypothesis and find the confidence interval. And then post our results. So we're not going to do the 5 steps for this one. We're going to say, all right, the null is equal to 24. The alternative is not equal to 24. So let's build a confidence interval. They had an average of 25.1 years old when they were first married. Oh, this is about the first marriages. So there were 50 couples they looked at. The mean was 25.1, not 24. And the standard deviation of the sample was 2.3. We do not have the standard deviation of the population here. We only have the sample standard deviation. So that means we don't get to use a confidence interval built on z-scores. We have to use the t-distribution. It's only one subtle little change, but that's because we do not have the population standard deviation. 50 is bigger than 30, so we could say, well, that's probably close to normal, but we don't have the standard deviation, so we're stuck with t, which is no big. The confidence interval then just is going to look like this. So we're going to look up t instead of putting a z-score there. It'll be a t-score, which just means we need degrees of freedom, which is 49. Oh, and you know what? I'm glad that was a weird number. 49 is not on your chart. 45 is and 50 is. Never round up. Always go lower. Always go to the more conservative degrees of freedom. So we're going to actually use 45 because that's what's on our chart. All right? So we look up 45 degrees of freedom and 95% confidence interval, and that comes out to be 2.014. So that's the only difference. Instead of like a 1.96 there, you're going to put a 2.014. All the rest of this is just the same as what a confidence interval with z would look like. All right, so let's see what happens. 25.1 minus 2.014 times 2.3 divided by the square root of 50 less than mu, which is less than 25.1 plus all of that stuff. I'm not going to write it again. We'll just say margin of error. All right. So we do 2.3 divided by the square root of 50. That gives us 0.325269. 2.014 times that. And so when we multiply those, we end up with 0.65509. And so let's take a look at that. 25 minus 0.655 is 24.445. And 25 plus that is 25.1, sorry, 25.1. Plus that is 25.755. So let's make our conclusion based on this. Is the null hypothesis included in this interval? The answer is no. It's just missed it, right? It's just to the outside. 24.4 is the lower bound, but 24 is outside. So that means reject the null. If the null is in the interval, you fail to reject the null and conclude that. If the null is outside of the interval, you reject the null. And then we would say, we would make our conclusion that there is enough evidence to conclude it's the average age of marriage is in 24. So we reject the null at 5% because it was a 95% confidence interval. And so, and conclude that the average age people get married is not 24. Be careful. Lots of students say, oh, is 25.1. No. This is a population we're talking about. This is just a sample. So we are making generalizations about the population. We're not replacing it with the mean of a sample of 50. It's just we know it's not 24 anymore. We need like further study to figure out what it is, if it's closer to 25 or not. But you can't make a generalization about a population based on a sample of 50 about the entire population. So that's why when we set up, that's why this is the first thing we do. And either we're going to say, nope, it's still 24, null hypothesis remains, or it has changed, but I just know it's not that. Or it's greater than that or less than that. It's a one-tailed test. But I don't know that it's this either. I just know it's no longer that. Right? And so that's a tricky part. So make sure you basically just restate either your null or your alternative hypothesis. All right? Okay. Next we'll do chapter 9.